Welcome back, everyone, to Neural Intel. Today, we're going to dive deep into something pretty fascinating about what actually happens inside a neural network when it gets really good at a task.
Yeah, it's a great question. Do the parameters, the internal knobs and dials, just find a sweet spot and stay there? Or is it, well, more dynamic?
Exactly. And we're digging into a recent paper that tackles this using some fairly advanced math. It looks at something called gradient flow.
Right, gradient flow. You can sort of think of it as the idealized, smooth path that the network's parameters would follow during learning, like continuous learning instead of the usual discrete steps.
Okay, so not quite the step-by-step stochastic gradient descent we usually talk about, but a continuous version for, I guess, a cleaner mathematical look.
Precisely. It lets them analyze the core learning dynamics. And they looked at standard setups, fully connected networks, common activation functions, logistic, TAN, soft plus, even GLU, like you see in BERT and GPT-3.
Okay, the usual suspects. And standard loss functions, too.
Yeah, mean squared error, binary cross entropy, the kind of things we use all the time. So our mission today is really to unpack the technical side of this. What does this research tell us about the mechanics of learning, and are there maybe some surprising behaviors hidden in there?
All right, let's get into it. What's the main takeaway? What did they find about this gradient flow behavior?
Well, the big finding is this fundamental split, a dichotomy, in how the parameters behave as the network learns. Essentially, there are two paths things can take.
Okay, two paths. What's the first one?
The first path is maybe what you'd expect. The network parameters converge. They settle down at what's called a critical point.
A critical point. So that's where the gradient of the loss function hits zero. Right?
Exactly. Think of it like a ball rolling down a hill and stopping at the bottom, or maybe a flat part. The network has basically stopped learning, at least locally, because there's no adjustment that immediately reduces the error further.
Makes sense. Find a good spot, stabilize. So what's the alternative, the second path?
This is where it gets pretty interesting. The second possibility is that the parameters diverge to infinity.
Wait, diverge? Like they just keep getting bigger and bigger, even
Right.
if the network is learning well?
That's the counterintuitive part, yeah. The error, the loss, it still converges to a specific optimal value. They call it an asymptotic critical value.
Hmm.
But the parameters themselves, the numbers inside the network, they just grow without bound.
Wow, okay. Parameters heading off to infinity while the network's performance is actually getting better and stabilizing. How did they figure that out? What math leads to such a split?
Yeah, it's pretty neat. The key insight involves this concept called definability in an O minimal structure.
Oh, minimal structure. Okay, that definitely sounds advanced. Can you break that down a bit?
Sure. It's a concept for mathematical logic, specifically model theory.
Mm-hmm.
But the essence is that the kinds of functions we use in these networks, these activations, loss functions, they belong to a class of functions that have very tame or predictable geometric property.
Tame? How so?
It means they aren't excessively complex. They can be built up from simpler pieces. And their shapes, their graphs, don't oscillate wildly or do other mathematically pathological things. This tameness, this minimal property, essentially guarantees that the long-term behavior of the gradient flow is limited. It has to either settle down or diverge in this specific way.
So this mathematical property kind of limits the ways learning can go, forcing it into one of these two scenarios, settle down or blow up.
That's a good way to put it.
Yeah.
And one really interesting consequence of this mathematical framework is something about reaching optimal performance.
Oh, yeah. What's that?
They found there's a kind of threshold. If you happen to initialize your network, like start it off with a loss value that's already super close to the absolute best possible value within some tiny margin, let's call it epsilon,
Uh-huh.
then the gradient flow is guaranteed to converge to that optimal loss value.
So start really, really close to perfect, and you're guaranteed to get there, at least in this idealized gradient flow world.
That's the idea. But, okay, here's where it connects back to the divergence thing in a surprising way, especially when we think about learning certain functions.
Like what kind of functions?
Polynomials. Think x squared, x cubed, stuff like that.
Right. What happens when a network tries to learn a polynomial?
Well, for any polynomial target of degree 2 or higher, so anything more complex than a straight line, and assuming your network is big enough and you have enough data, the researchers proved something pretty striking.
Okay, what is it?
The loss function can never actually reach zero. The network can get infinitely close, arbitrarily accurate, but it can never perfectly replicate that polynomial function globally.
Never hit zero. Even
Okay.
with a huge network, that's interesting. Why not?
It ties into the nature of the activation functions, which we'll get to. But the implication is The absolute best is only achievable, like asymptotically.
Okay, so it keeps getting closer but never arrives. How does that link back to the divergence?
Right, to combine that, finding that zero loss is impossible for these polynomials with the dichotomy we talked about. If the network starts off really well, with its loss already below that critical epsilon threshold,
Yeah.
then, since it must converge to the optimal value, which is zero loss in this case, but it can never actually reach zero loss, the only way for the gradient flow dynamics to satisfy both conditions is for the parameters to diverge to infinity.
Whoa. Okay, let me see if I got that. Because it has to aim for zero loss since it started close enough, but it can't actually reach zero loss because it's a polynomial. The parameters just keep adjusting infinitely, growing larger and larger as the loss gets closer and closer to zero.
You nailed it. That's a surprising conclusion. The optimal parameters are effectively at infinity. The network just keeps chasing them.
That's a really neat technical insight. Does this depend on the specific activation functions used?
Absolutely. The type of activation function is critical here. The paper introduces this class called sublinear analytic definable functions, or SAD functions for short.
SAD functions. Okay, what makes a function SAD?
Three things. First, sublinear. It means the function grows slower than a straight line for very large inputs. Think like logistic or tan, they flatten out.
Okay, sublinear. Got it.
Second, analytic. This means the function is super smooth. You can represent it with a convergent power series locally. No sharp corners.
Right. Infinitely differentiable.
And third, definable. That's the O-minimal structure property we talked about earlier, ensuring that geometric tameness.
And functions like logistic, tan, soft plus, GELU,
Yeah,
they all fit this SAD profile.
exactly. And that sublinear part is crucial for the polynomial result. It's what fundamentally prevents a network built with these functions from perfectly matching a polynomial of degree 2 or higher everywhere. It can get really close on your training data, but it's mathematically impossible for it to be the exact same function globally.
So the network is always just an approximation. And because it's analytic and definable, the math sort of knows it's not a perfect match, driving this endless adjustment towards infinity.
That's a great way to think about it, yeah. The mathematical structure prevents a perfect match, and the optimization process keeps trying to bridge that impossible gap, leading to diverging parameters.
This is fascinating, theoretically, but did they actually see this happen in, practice with actual training?
They did. They ran numerical experiments to back this up. They trained networks specifically on polynomial targets
Yeah.
using standard optimizers like SGD and Atom.
Did the parameters grow?
Yep. They saw a very clear trend. As the training loss went down, meaning the network was getting better at matching the polynomial, the norm of the parameters, which is basically a measure of their overall size, went up, often quite significantly.
Okay, so the theory holds up in simulation.
And interestingly, Atom, which is known for being pretty good at adapting learning rates and handling situations where gradients might get small, show this effect even more strongly than plain SGD.
That makes sense. And did they look beyond just polynomials, like more realistic tasks?
They did. They extended this to a couple of more complex scenarios. One was using networks to solve partial differential equations, using something called the deep Kolmogorov method.
Okay, complex scientific computing tasks.
Right. And the other was standard image classification on the MNUST dataset of handwritten digits.
And they saw the same thing, parameters growing as loss drops.
Remarkably, yes. In both cases, they observed this tendency for the parameter norms to increase as the loss decreased. It really suggests this isn't just some theoretical curiosity limited to learning polynomials. It might be happening quite broadly in deep learning when pushing for very low loss.
That definitely feels like a significant technical observation. Are there catches, limitations to this analysis?
Oh, for sure. It's important to be clear about the boundaries here. The really strong theoretical results, the proofs, are specifically for gradient flow that idealize continuous time learning.
Right, not necessarily for discrete step-by-step SGD or Atom that we actually use.
Exactly. While their experiments show similar behavior with SGD and Atom, proving it formally for these discrete optimizers, especially in this regime where things are potentially unstable because parameters are diverging, is much harder. It involves dealing with the Hessian matrix, the second derivatives, and its behavior, which gets complicated.
So the math is solid for the ideal case. Bridging it perfectly to practical optimizers is still ongoing work.
Pretty much. Another key point is the activation function requirement. The analysis relies heavily on the functions being smooth, continuously differentiable, or even analytic.
Which means Real you knew is out.
Right. Real U with its sharp corner at 0 isn't covered by this specific analysis. In fact, they point out that for real U networks learning polynomials, you can sometimes find actual global minima with finite parameters, so the divergence result doesn't necessarily hold.
Okay, so the type of activation really matters for whether this divergence happens.
Definitely. And also things like adding L2 regularization or using weight decay in the optimizer technique specifically designed to penalize large parameter values would likely prevent this divergence behavior as well.
Got it. So it's a specific phenomenon under certain conditions, primarily smooth activations, no strong regularization, and aiming for extremely low loss on tasks where perfection might be asymptotically achievable but not finitely reachable.
That's a very good summary, yes.
Okay, so wrapping this up, what are the key technical takeaways for our listeners? It seems like really pushing networks to the limit of their performance, especially on complex mapping tasks, might involve this perpetual state of parameter adjustment.
Yeah, and potentially leading to these incredibly large internal parameter values, even if the network's output looks perfectly stable and accurate. It's a different way of thinking about what convergence means.
It definitely adds a layer beyond just watching the loss curve go down. You have to consider how the internal representation is evolving, too.
Absolutely. And I think the connection they drew to O-minimal structures is just, well, really cool. It shows how these quite abstract mathematical ideas can actually give us concrete insights into these very complex engineered systems.
It does underscore the deep mathematical foundations underpinning AI, and seeing this divergence pop up in simulations of practical tasks like MNIST and PDE solving raises some interesting technical questions, doesn't it?
For sure. Like, does this unbounded growth have any practical consequences down the line? For model stability, maybe for generalization, or even interpretability? If the numbers inside are astronomical, what does that mean?
Right, exactly. These are the technical puzzles this kind of research surfaces. It really challenges our intuitions about learning dynamics.
It's a fascinating look at the interplay between optimization, the function being learned, and the mathematical nature of the network itself.
Well, this has been a really insightful deep dive. It certainly gives a new perspective on neural network training. For listeners who want to really get into the weeds, the original paper is linked in the bio on our webpage. You can find that link, along with links to other recent AI and ML research papers there, too.
Definitely worth a look if you're into the mathematical details.
So, thinking about this divergence, what new technical questions does this raise for you about how we train and understand these models? Something to ponder. That's our time for today on Neural Intel. Thanks for joining us.